So today I want to share some tips and like things that we have learned over the years by designing systems for very high performance. Like performance and security are two issues that keep coming up often again and again. And these are two kind of skills that take like quite a lot of time to like adapt to. So like I just want to get up to speed to those who are like relatively new to this domain. So we'll start. So first I just want to share this. This is like a screenshot from Microsoft about like, this is a video that they took down, by the way. This is a video where they show like how fast their new Teams is. So MS Teams, how many of you have used MS Teams? Oh, like 50% of you have suffered this, okay, great. So again, it used to take 22 seconds to start, and after some improvements, it now takes 9 seconds to start. They uploaded this video and then they took it down, but like internet parodied it quite well. So like they did not see the parody there that like 9 seconds to start an application is insane amount of time. Like our standards have stooped so low over the years. And like one of the best tweet on this was like modern software performance is firmly in its beyond parody stage now. And if you guys know, if you follow Casey Muratori, you know like he's like very wild about performance. So we'll try to understand how this has happened over the years and how we can get better at this. So like I want to talk about mostly like 4 or 5 kind of things where like how to build high throughput ingestion systems or a very high number of concurrent users or like heavy amount of batch processing or read-only traffic. So like all kinds of weird use cases that you hear from customers are like, can your system do this? The answer is usually it depends, and like it depends on how well we have designed it or we will design it. So we'll see that part now. Like the rough goal of mine is like you'll be able to understand like how to get the best bang for your buck within the bounds of Frappe Framework. So like I'm not suggesting you to rewrite everything in Rust or like do microservices or anything. Like these are just basic principles for achieving high performance. So by and large, there are 2 ways of achieving high performance. One is you design things for high performance. The other is you design things willy-nilly and then eventually optimize things for high performance. The hard reality is like the designing is not optional. Like if you don't design things well, or if your like initial iteration is quite bad, then you will not be able to recover a lot of it. And which is what you see with Microsoft Teams. Like once you have reached 22 seconds of startup time, you are not going to go back to 1 second very easily, or like maybe ever. So like the thing you have to consider here is like this is not at all optional, and whatever sins you have committed, you can only recover from part of it. And the most core concept here is like whatever you design, it has to be parallel first these days. How many of you have seen a graph like this before? Just like a show of hands. Okay, very few of you. So this is a graph of how hardware has evolved over like last 30 or so years. So in 1975, Gordon Moore predicted that like every 2 years, or which later became roughly every 18 months, the transistor count on your chip will double, which means roughly every 2-ish years, your performance doubles without doing anything in software. And if you see the transistor count, that has kept going up and up. Like that has only, like this graph is slightly old, that has only stopped like in the last few years. And now it is quite costly to add more transistor on the same chip. That is called Moore's law. The second important thing to consider here is the single-threaded performance. So when you don't run multiple workers or anything in parallel, what is the improvement over time we see from hardware alone? So if you see like the hardware performance kept improving until roughly around 2005, and then it kind of plateaued and it hasn't improved much. So if you have had a computer in like 20 years ago, it was probably some Pentium with 3 gigahertz. If you get a computer today, it's probably some Intel i3, whatever. It's still 3 gigahertz. Like the clock speed we have plateaued, single-threaded performance we have quite plateaued. Like it's not doubling. So whatever you do these days, like the only thing that is scaling these days is number of cores. So you can parallelize your workload, but there is no other way out of getting more performance out of hardware. And so the scaling that stopped is called Dennard scaling, if you want to look it up. It was quite a fundamental shift in how we design software for performance, because we weren't getting any more performance hardware anymore. And this is 2005, and a lot of software we design today still does not consider this basic fact that these things have to be parallel first. Like it's not at all optional. And the scaling obviously moved to number of cores. Like back then we had single core or dual core, and now we have like 32 cores on laptops. So it is quite crazy. So modern hardware is again all about parallelism, and we barely utilize any of the capability of modern hardware. Like even on EC2, whatever machine you are getting is some kind of epic server from AMD. And we are not, like our software is just not there. So if you think about just like our Frappe stack, we use Python. So the day we made the choice of using Python, we have said we are accepting 100x slowdown on a lot of things. So, and there are obviously some merit to that decision, like we are getting a lot of flexibility, the development speed, but at the same time, like if we keep making those bad decisions again and again, eventually everything will be so slow that like your customers won't be happy with your software. Both Dennard scaling and Moore's law are dead, so like there is no hardware is not going to help you for like 5 to 10 years easily, unless something miraculous happens. And LLMs definitely won't save you. Like they are trained on the crap code that we have written so far. So just like don't have any hope from there. So like hopefully I have convinced you that like parallelism is kind of important, but parallelism is definitely not easy to achieve. Like any kind of parallelism you try to, like if you take any simple single-threaded code and try to write it in multi-threaded mode, you're going to, like you're not going to get like linear scalability. Basically like adding more CPU cores does not magically make it like twice as fast, because there are obviously things like you end up introducing some bugs, so like you have to obviously worry about correctness. But apart from that, like there is contention, synchronization, coherence. Like so, when you have parallel code, they are obviously competing for some shared underlying resource, some hardware resource or software resource. And if you have not designed it properly, then they are probably just wasting time contending on something. Parallel code also has to synchronize with each other. Like they can't just run in parallel without talking to each other. So like that synchronization has some overhead. So we never get like this linear scaling, which is like utopia. Like usually we get some diminishing returns, and in practice we even get like severely bad results if you like overdo it, which is called USL if you have to look into it. So like now like unrolling all of this theory and coming back to like some Frappe context, we have roughly like all of our workloads kind of fall into two categories, like interactive workloads and batch workloads. So, and interactive is also again mostly web request, like whatever user is interacting in browser, which is for framework that would be your list view, form view. For other apps it could be, like, which is similar, like mostly it's just list view, form view everywhere. So like those interactions are your interactive workloads, and the batch workloads are heavy kind of processing that goes on in background, like generating reports or processing some kind of account postings, etc. So we'll deep dive into these two type of workloads and how to specifically optimize for each of them. So first we'll look at interactive workloads. So interactive workloads, the sort of gold standard for interactive workloads is like any kind of request or command. Like this is not even request. So this thing is called duality threshold, where like any interaction with computer, it is supposed to give you back a response in like 400 milliseconds or something. So this is where the shift occurs when like you start talking about milliseconds. Like no, you should not expect a response, interactive response to come in seconds. It should be 400 milliseconds is the like the top limit that you should have for like any kind of read-only request or any kind of recurring request. Like if you open a list view, that request should finish in 400 milliseconds. If you press a button, it is supposed to do something interactive, it should finish in 400 milliseconds. And this is not just a cooked up idea. Before this guy came up with this number, that was quite high, but like this number is still from 80s. And IBM research figured out like 400 milliseconds is roughly the time where like user feels like they are interacting with something in real time. Like it's not like computer is not slowing them down. So you want your software to your users to like work at their speed of thinking and not like slow down so to accommodate your software. So this should be the standard. We achieve the standard in most frequent requests, and like we eventually fix wherever we don't. But we don't see this in a lot of custom code where like not much thought has put into it, and often it is not a cause of concern, but eventually when like you have 100 users trying to interactively do something and they are all spending 2-3 seconds to like click something and get a response, you are degrading user experience quite a bit. And they will not complain. They may not complain, but like they rate your software poorly. They will only complain when it completely stops working. They do not complain for like minor degradation. So we'll look at how to beat this. And the first basic thing is it's just impossible to beat speed of light. Like let's say you are in New York or something and you use Indian servers because Indian servers are cheaper. You have just bought like 300 millisecond into your 300 millisecond of guaranteed latency in your system. Now you only have 100 millisecond left to do your work. So like don't make your job harder by trying to optimize cost where you should not. Like just get the server nearest to you, and we will hopefully cover more and more regions anyway. We anyways cover quite a lot of regions. Like so, most regions you can get less than 100 millisecond from anywhere in the world. So the other thing that you should consider, like the first is obvious, like while designing, you just make sure that like whatever you're doing is within 400 millisecond bound. But the other thing is when you are developing something locally, your databases size will be in few megabytes, and you will not anticipate what happens when that size grows. So the other thing that you should do is like for any kind of frequent interactive workload that you expect, you should design it from P99 or P90 latency perspective, which is what will happen to the 1% of the worst request that will come to this endpoint. So for example, this is a very basic, simple example where we are showing like how many invoices are there for a particular order. And we are just counting, we're just doing property.db.count for against this order, how many entries are there. Now this seems very simple, and locally this will be like 1 or 2 milliseconds usually. But what happens is like this query gets translated to like very simple select count star where order is whatever the current order is. But the problem here is like if order is not indexed, like you are scanning the entire invoice table every time just to show the count. So if you just build this locally and never think about what will happen when this size grows to like 100x or 1000x of what it is on your local machine, then the slowdowns will occur and they will get reported and you will have to eventually fix them. But understand the difference here. Like when they get reported, it's not going to be reported for degradation of like 1 or 2 seconds. They are going to report it when it takes 60 seconds and it does not work. So like you have like months and months of degraded performance where your user believes your software sucks, but they do not complain. The one important thing to understand here is like SQL is quite a leaky abstraction. Like it gives you very nice declarative language where it just gives you the result that you want, but it does not give you the same kind of guarantees for performance. So you have to design schema indexes from day one to have the required performance. And here, like it's very clear that if you don't have index, it's just going to take linear amount of time with the size in your table. So again, like I just want to reiterate this point, and I'm going to reiterate this again and again. So I did not mention anywhere how to profile SQL queries. This is you don't even bother profiling SQL queries. Like you start with understanding this query is going to be frequent. It should have an index from day one, and then you never run into the problem of having to profile slow sites. But it's quite hard. But like if you start doing it, it's not impossible. So going back to the interactive workloads, the other thing that we do to improve interactive workloads is you need to cache things very aggressively. So this is like how a typical request goes from your user to a server and comes back to the user. And in between, you have like two Nginx proxies. One is just a transparent proxy. There is one app server proxy. There are web workers. There is DB server, and there is also cache server, which is Redis. So there are lots of moving components here. And the more component you try to involve into the process, the more likely it is that your request time will not be deterministic and it will be slow. So there is opportunity to cache things on every layer. Like, so you can design your caching to be, like for example, Raven probably caches on the client side itself. Like it does, for a few things, it does not even bother sending a request to server. Like it has the necessary data in local storage or, I mean, front-end folks might know what that is exactly. But you can cache things in browser. You can cache things on Nginx proxy, which any kind of public file. You can cache things on Frappe workers with V16. We have client caching. You can cache things on DB servers also. Like if you have very complicated computation, you can compute it once and store it in DB server. And you can also cache things on cache server with like few lines of code. Now the problem here is like you run into the two hardest problem in computer science, the cache invalidation part. But that is not optional. Because of the architecture, like most web apps are written like this. And maybe there is some research where like we won't have to worry about cache and cache invalidation, but right now it is the reality of life. Like you can't just avoid caching because cache invalidation is hard. So there are some recipes here, like any kind of pre-computed results you want, you can store it in Redis or database. If you have some documents that do not change, instead of using getDoc, you can use getCacheDoc. It's just using Redis, but like you just added like 6 or 7 characters, but it got like significantly faster. Then metadata or something about schema or something, some settings that never change, you can also cache them in client side. So which is a new thing in v16. Maybe I'll talk about it separately. And lastly, if you have any frequently accessed API, you should use the HTTP cache header, where like your browser does not even bother sending a request; it just has the data locally. So that was about those were few tips for designing for interactive performance. But the most common issue in interactive workloads is some kind of contention, and this is often hard to picture at first. But if you just like look at what goes on in your workload, you can probably spot where it can contend. So I'll just give you one example here. Let's say we have a very basic API. This is just inbuilt API where we are ingesting IoT logs from like all sorts of IoT machines. And IoT, all those devices, they don't know or care about what is going on in the server. Like whenever some event happens, they are just sending the log. So they are not aware of the workload or anything. They are just doing their job. Now, what can happen here ideally is like if you have like a 4 CPU machine, let's say, and if you have 4 separate workers, ideally our design just has everything parallel, so you don't have to worry much about working about parallelism here. All you have to worry about is like, is there some contention point which is probably preventing this kind of parallelism? And this is something what people would call like embarrassingly parallel workload. Like there is nothing that in here that prevents it from being parallel. But like in reality, that often does not happen. So if you, I had a demo, but like right now you just have to do with the GIF of the demo. But basically, I replayed that API with a lot of I tried to bombard our site with a lot of traffic, where workers are trying to ingest things. And if you see here, like while ingesting a log, there are mainly 3 steps in that process. We get the data, we name the new document something like log-1 or something, and then we process that document and then we store it in the DB. So if you see what is happening here is, like at any time only one worker is processing something. Like only one worker is processing something, all the others are doing naming. And if you have never seen this before, it feels quite weird. But like if you think about, if you go and look into how naming works, like I'll show you this. So this is how naming works. Like if you have a naming series where like you have some prefix, IoT-log-something, and you want to have guaranteed incremented counters. So like 1, 2, 3, 4. Like you do not want any gaps in between, or you also don't want like multiple documents to have the same number. So this kind of counting numbers is inherently a sequential process. You cannot count numbers in parallel. It's basically impossible. So the way we do it is we lock the row, which is counting the current number. And what happens is like whichever request came first, that has the lock. And until that is processed, no one else can even count the next number. Even though like naming has already happened, but until the whole thing is processed, you cannot move forward. So this is an example of like having hidden serial chains where visually you don't see that this work is not sequential. Like visually it appears, oh, you have 5 workers or 4 CPUs and 4 workers, and it should all be parallel. But in reality, it is all happening sequentially, and it is often very hard to diagnose this just by looking at it. But the few things you can do is like just load test and keep monitoring process list and other resource monitors. And if anywhere you see some kind of contention or wait time, then most likely you have some contention there. So that's mostly about the interactive workloads. I'll move on to batch workloads. So the biggest sin when people commit while doing batch workloads is they try to run batch jobs in web request, and then everything goes to shit. The reason is quite obvious. Like you have certain amount of web workers, and even if you had like even if you like triple or even if you get like 10x number of that, the moment you start running bad jobs in your web request, they are going to get blocked for a prolonged period of time. And the longer they are blocked, now your other users can't do interactive work. And this is why we aggressively move reports from UI to prepared report. And I keep getting pinged for like, why do you have this threshold and why can't I disable prepared report? Because it's a bad idea to run reports in web request. Like even if they take like 10 seconds, it's still a horrible idea. So I'll give some simpler example for batch workload first. So most documents do not take much time to submit, like they might take 1 or 2 seconds, but you might have some documents that take a lot of time to submit. And this was a feature we introduced in V14, I think, where like users does not have to submit the document synchronously. Like if all they care about is submitting a document, they can just request submission and eventually it will happen in background and then user will get notified that it has happened with Socket.io or some real-time event. So the idea here is like you have to identify what operation does not need to happen synchronously at all, and then decouple it from your web request and do it asynchronously. Now this is not going to be simple, obviously. This is all of this extra wiring of web request to background workers. It's going to complicate your system, but it's going to make your system more robust to those like spikes of workload where like 10 people are trying to submit something and now other 10 can't use your system at all. So this is like deferring all of the heavy work to whenever it is possible to do in the queue. So another important concept to understand here is like you have to right size your batch jobs. So your batch jobs should be roughly in between 10 seconds to 10 minutes. They should like even though we allow hours of time, you should not write jobs that are so large or so small. If you write jobs that are quite small, like 1 or 2 seconds, then you run into the problem of like wasting time setting up that job, tearing down that job, and doing very little real work. If you have very long running job, then you have this problem of starvation. Like if you have, let's say, hours, or if you just end up queuing some jobs that take hours, then nothing else gets to run. So like the same problem that happens in interactive workload eventually creeps into your background workloads also. So ideally, just try to keep it within 10 seconds to 10 minutes. It's easier to remember. I'll show some examples here, like what kind of optimizations or design changes that you can do to avoid these kind of things. And these are some of the things that we have done later when we realized that we have screwed up on some of those designs. So the most basic example here is in accounts module, where if you have to compute balances of any account on any day, you basically have to write a query like this, like give me sum of debit and debit minus credit for all of the entries for this account. Now, obviously, this is just proportional to how long you have been using the site. So on day one, it is few microseconds. And by that, if you are a heavy user, then by the time your first year ends, this is quite slow already. So this design is just not scalable. Like if you have to think in terms of like bigger numbers, this is O of n-ish design. And what we want is not scan the entire data every time you have to get balances. So the solution here is caching only, but the caching is it's not dumb caching that we just do, like we slap Redis cache and store it in Redis and just get the answers back. You have to implement some business logic concept here. So in accounts, for example, you close the balances at the end of each month, or at least hopefully at the end of each year. So wherever that becomes your checkpoint then. So whenever you close the books, we can also cache the computed result for that period, which we don't have to compute again and again. So in this design, we obviously limit the time to proportional to time since whenever we close the last time. Obviously, this is not bulletproof because some folks, for some reason, never bother closing books. But so other typical use case that comes up is what to do about like those frequent tasks that take 1 to 10 seconds, like you are trying to ingest like lots of documents from API. The first obvious solution is like you just move it to background jobs, and that works. But if they are so small, then maybe even just moving everything to background job will not be good use of your CPU time, because you will be again wasting a lot of time setting up and tearing down. So the most common solution here is whatever you want to process later, even though it just takes 2-3 seconds, but you have to process a lot of it. So you have to batch those workloads. And computers are magical when they get to do the same work again and again. Like they are optimized for that kind of work. So if you have a lot of documents to process, you just ingest them once and you temporarily store it somewhere in some kind of queue. So like framework has a deferred insert, which is available by default. Some patterns are replicated in other places. Like email queue basically works that way also, where we don't immediately send your email, we send it every 4-ish minutes, and we just stage it somewhere. So if you take example of email queue, like if we had to open SMTP connection for each email connection, then we would be spending quite a lot of time just opening connection, sending something, closing connection. And the email servers also don't like doing that. So you have to batch your work somehow. And that somehow is different for most use cases. There is no just generic design or answer that solves it. But the pattern is like this, where you store something in some temporary storage, then you consume it over with a background flush mechanism. Other mechanism is when you have a workload that is just not possible to do in one job, you have to chop it and batch it somehow. So this is an example from ERP Next, where we are trying to, and this is bill of materials for, like short explanation is like bill of materials is anything that you manufacture, like a laptop, you have components which are like keyboard, and those components also have subcomponents like individual keys. So you have all of these tracked separately, and whenever you want to update cost of all of them, you kind of have to go bottom up in a tree traversal, like I'm giving some DSA. So you have to traverse the tree from bottom to up, and you have to process all the documents. Like you can't just do like, you can't just randomly process documents, because the cost of the parent assembly depends on the cost of the child assembly. So the way we solved, like the way we used to solve was like we'll just process all of them in the same job. We just have 25 minutes to process, and we have plenty. And typically companies do not have that many bill of materials. That's the thing, like locally your machine does not have that many bill of materials, and most companies also do not have that many bill of materials. But we had one customer that had 10 lakh bill of materials, which is impossible to process in 25 minutes. And the solution is not to just like keep increasing, okay, maybe it is possible to solve in 2 hours. That's a bad way to do engineering. So the way we solved it is we split the job into, first we construct some version of this tree, and then we figure out like which part we can process in one chunk. And one chunk would be, let's say 5,000 or 10,000 documents. It is still quite a lot, but it's not 10 lakh at the same time. So when we can split the job naturally like this, then you at least make some progress. You are not trying to process 10 lakh document and fail and process it again and fail. You are making some progress, which is guaranteed, and eventually you will do the whole job. Now that eventually might depend on how good your code to process that is, but that's a separate topic. The last basic example here is like if you have to process a lot of things, and if you're just processing like this, like a single job where you get a whole bunch of document, like this example is very recent example of help desk where we want to close old tickets that are older than certain days. And the feature was introduced after the fact, like it wasn't there from day one. So like even we had like thousands of tickets that were not closed. And every 4 minutes, we attempted to close all thousands of tickets. We ended up achieving few of them, and then we failed, and then we roll back and start over. So this has what happens when this has 10,000 tickets is this just fails, and it just goes into that same loop of trying to do some work, not being able to do it, rolling it back and starting again. So checkpointing is the most important way of fixing these kind of problems, and checkpointing is often just as simple as just committing after doing the atomic amount of work. And this also gives you small transactions. Like databases do not like transactions that run for hours and hours, because they have to provide you a snapshot of some database version. So they do not like very long running transactions. So committing often is useful. At the same time, if you don't know what you are doing and you commit in random places, it can result in very horrible bugs, which are next to impossible to debug without reading the code and imagining. So like there will be some disclaimer on this from Rohit's talk, so I'll not bother explaining all that. So lastly, like I have covered interactive and a batch workload. So a few notes on scaling without going much into detail about optimizing or anything. Start by scaling by credit card, which is like obviously a cloud company saying just give us more money. But this is the easiest thing to do, because if you have some problem, don't get into the idea of like you can just fix it immediately. Like start by reducing the impact first, which is let's just get a bigger machine. And if you can, and while getting a bigger machine, at least ensure that you understand where you are contending or which resource is bottlenecked. And which is usually quite easy by just eyeballing the monitor, like a Frappe is monitoring output. And if you do that, then most likely you will survive another week. But if you don't survive another week and you have to constantly do it, then you have a bad problem at your hand. The second way to scale is obviously horizontal scaling, where like we provide a option to set up replicas, and that takes up quite a lot of your load on the main database servers. And we also suggest, like, this is a very special case where like if you realize that some part of your design is just so bad that it does not fit in Frappe architecture, because like Frappe architecture is not like a silver bullet that will solve all of your problems. So some of the problems, like for example, let's take example of Frappe Cloud, which runs on Frappe Framework. But we don't do that. We used to do the builds on the same server in background job, which we eventually realized is not a good idea, because we have to build like hundreds of new Docker containers every day. We can't do that on the same server. So we offloaded to a separate service. We wrote a separate like server, which build servers, which does our job, and you get the results back. So it's not like you can't do microservice. Like this question keeps coming up often, but you should do it for like very specialized use cases, not the wild west that you see on internet. Lastly, like this is just one hilarious thing about hardware. Understanding how hardware behaves is kind of important. So when you see something like this, like I have paid for 100% of CPU, so I'm definitely going to use 100% of it. You can, but you will suffer. It's often hard to convince why this is a bad idea. So the way this goes is like the moment you start to hit 50 to 60% utilization, what you see here is average, and there are quite a lot of spikes in the middle where like user is just stuck waiting for seconds for something to happen. And you don't see those in like these pretty average charts, because over time like small spikes get averaged out. But if you look at like the different relevant charts, like how much time some processes were waiting, you see these clear spikes over a long time, where like every hour something is happening and your users are facing some problem. So you kind of need to think about these things like quite early on. You can't just leave it to retrospective analysis. And again, lastly, I just want to reiterate the same point. Like designing for performance and optimizing for performance is quite different. So as much as you can, you should shift left. Shift left is like you move these problems earlier in your software development lifecycle. You don't retrospectively try to fix this. And that helps with customer satisfaction and retention quite a lot. And I also understand like the question that I got internally was like, all of this is quite complex. Like why can't we just like expect Frappe to handle a lot of this? Because Frappe gives you the building blocks, but it cannot just give you like generic solution for all kind of problems. And eventually we will come up with different solutions, but this is a complexity that is required. Like there is a concept like a certain kind of complex problems, they require equally complex solutions. Not all of them have simple solutions that just work out, and you have to invest in those things. So that's all from me. Like go write some fast systems. And lastly, one more thing so like I worked on performance for like last 3 months, and like we benchmark quite a lot of frequently used things, and V16 is roughly 2x faster now. Like a part of that contribution was from Sagarura. A lot of it, majority of it was from framework, but like it is possible to achieve this much speed up after so long, which tells you that there are some low-hanging fruits which we could have spotted long ago, but we are now retroactively fixing them. So hopefully you will like V16. That's all.